All right, guys, video 2, got this queued up where you should have the visual inspection workshop PowerPoint that I had for you pulled up. This is one I did, and it's going to go over everything we talk about here for the different types of discontinuities that we're going to see on welds into a lot more depth and a lot more detail. So, you go past the title page, things we're going to cover quick, and this will be a two-part one. Will be key terms and definitions, types of discontinuities, the AWS D11 Clause 6, and that's actually been changed with the new 2020, but we'll cover that later. Different types of inspection tools, and Q&A, and you guys don't have to worry about a hands-on test. So, next slide. Terms and definitions. Everything we're going to be talking about this is going to be coming out of the AWS 8 3.0. The version I have is the 2010 edition. The reason that we're doing this is to make sure everybody's staying on the same page using the exact same terms. Things we've talked about before is that depending on what industry you're in or where you come up from, you hear some non-standard terms and it can lead to confusion. I'm going to try to eliminate as much of that as possible. So, we talked in the last video, short one, about the difference between discontinuities and the difference between defects. So I'm not going to go into that too much right now. We've got to talk about code requirements and contract documents. Now your code is going to define what actually makes something a discontinuity or a defect. Remember that a discontinuity is something that's a flaw in the weld in one way, shape, or form, and a discontinuity is, or a defect is when that flaw gets to be so big. So why are these things so important? Well, I'm going to do a little experiment with you guys. I want you guys just basically get a plain sheet of paper somewhere, okay? So we're going to take this plain sheet of paper. I want you to hold it out here on the edges and do your best not to wrinkle it and pull. Now you can do this, and you can actually put, depending on how strong your paper is and how high quality, you can put a lot of weight there on the edge, okay? This is an example of a good weld. So now, what I want you to do, put a little rip in there. This right here, the engineering term for that is called a stress riser. And that's actually what all of these different types of discontinuities are, is they're stress risers. What that means is that is an area where stresses will be focused and amplified. So now we're going to do the same thing. Make sure you're holding it all the way up here on the edges. And just give her a little pull. And for a fraction of the strength that it took last time, it'll rip. Now for those of you who got to rip last time, if you do get one of these to rip, you're going to be gripping way up here and it's going to rip in the corner. Well, the reason that it's going to rip in the corner just like this is because instead of being nice and smooth as you're gripping it trying to pull, you end up wrinkling it. Those wrinkles, even just not just a tear, but even just wrinkling the edges as you're holding it, can greatly reduce the strength of that piece of paper. So the tear is a big example of a discontinuity, but even small ones, like I said, just wrinkling that paper in your fingers as you're squeezing it can greatly reduce the strength of that weld. Now, your code requirements are going to say what's good, what's bad. Now, code requirements, once that's invoked, it's a legal document, and that is actually your bare minimum. We can always add to, we just can't take away from. When we get into that add to, that's when we get into your contract documents. You're making something for somebody, they may say, you know what, here's our base code, but we understand the structure, but we don't want any arc strikes, or we want less undercut, or we're going to give you a little bit extra reinforcement, but we're not going to give you any under. All that, as long as it's all agreed with in the contract documents, is exactly what you got to follow. Remember that the code is the minimum, but whoever is going to be responsible for that product when it goes out into the real world, it gets put into use, whether it's a trailer, whether it's a vehicle, whether it's a bridge, whether it's a building, all that responsibility for making sure that those work fall on the end user. So I'm going to go to the next slide here. The different types of discontinuities, talked about a little bit, but porosity, incomplete fusion, inclusions, inadequate joint penetration, arc strikes, overlap, undercut cracks, and underfill. And then we're going to have our 3 failures of the base metal, which are laminations, delaminations, and laminar tears. So next slide again. So the first one we should have discontinuity. Now this slide right here, what you see is we have the caption says align porosity with cracks. All this is there's basically a holes in the weld. Well, those holes in the weld or any sort of porosity is just gas that's trapped in the base metal. And anything that's trapped in the base metal that is not both weld metal and or base metal is what? Well, it's an inclusion. So that's actually what we got going on here. Porosity is a gas inclusion, okay? And it's going to be the most common type we see. If we're seeing this with hardwire type welding, usually that means that we've lost our gas shielding. If we're seeing this with stick welding, means it's almost always an indication of long arcing. Other types of, depending on the placement and what it looks like, other ways that we're going to see this or could be base metal contamination, especially hydrocarbon contamination in aluminum. Now, this one here is a little trickier to see. Now, you have to look inside there, but there's what we call these worm tracks. Now, this is a indication of, you see this mostly in flux core welding, so we'll be talking about that next semester. But it's just it'd be a little pinhole with a track behind it. And that's an indication that you're running too short a stick out. When you're doing that with a flux core, you got to give that a long stick out. Let that wire get time to heat up and give that, that flux time to burn. What happens if you get too close to it, that flux will start burning still inside the weld. It'll boil up and trail in behind it, leaving these perfect little tracks in there. The other indication that you'll see with this is that that weld will be, or if that wire has been allowed basically to get wet. And you get a little bit of steam inside there. We don't see it too much around here except in the summer. It can get that way if your stuff's allowed to sit out. Down south, real big issue. All right, moving on to the next slide. This one says scattered porosity. This is your gas outs. You guys have all seen this. You've all done it. You all know exactly what this is. We've lost shielding gas for some way, shape, or form. And piping porosity. This is when you have welds down. I have itty bitty little pinholes that come up to the top, but the weld itself underneath it has a lot of, is basically nothing but holes. If we were to cut into this, that weld would basically be just cavernous underneath there. This is almost always an indication that you have some sort of root contamination. So the top of the weld looks okay, except for a couple little pinholes, but when you cut into it, it's just garbage, absolute garbage. Okay, incomplete fusion or lack of penetration between the base metal and or adjacent weld passes. This just means your welds didn't melt together. So, what does that mean? Well, this can be caused by a couple different things. One of the very first problems that this is going to be is because you're too cold. How many times have I told you guys that cold and slow will cause you way more problems than hot and fast? This will end up causing you to have things that just don't work. They may kind of look good, but there's no fusion there. That weld is just sitting on top of the metal, and you might even be able to knock it off. You guys saw this a lot when you're doing your vertical downs, because that weld just sits on top. That is a classic example of lack of fusion. If you're doing this on a multi-pass weld, that can happen as well, where just one pass doesn't fuse with the others. One of the other reasons that can cause this is being in the wrong polarity, especially with hardwire welds. If you're supposed to be welding in DCEP, which is where most of our hardwire welds are, and for some reason you're in DCEN, that weld will not bite. You can almost go and peel each individual layer off the pliers. I used to have one of those before the fire got lost, and I haven't been able to quite recreate it. but yeah, it's a bad deal. Most of the time, again, this is too cold, not near enough amperage, not enough voltage, depending on which sections you're on. But that is something else to watch, that if everything else looks good, you may be in the wrong polarity. So, next slide. This is incomplete fusion. This one here is actually done, the slide you should be looking at says figure 2.6, incomplete fusion. This is actually a plasma arc weld. What a plasma arc weld is kind of like a TIG weld, except instead of being having an electrical arc, it's got a plasma jet in there. And works wonderful for stainless steel, especially relatively thin stainless steel. But right here, they just missed. And so he was off to one side, and two sides didn't melt together. Yep, incomplete fusion. Other one, this one is, you see that nice dark line right across the top there on the next slide. Incomplete fusion between the weld beads. Lots of spatter on there. That's just a classic cold weld. This is also another version of overlap. We'll talk about that later. Another incomplete fusion. Now on your groove face, this is where especially when you tell me that on a cap pass, on a groove weld or any sort of multi-pass weld, if I can find the edge of that weld at any given spot in time, that is absolutely incomplete fusion. The whole weld is not tied together, and that is an automatic fail. And unfortunately, I have to fail a lot of people for stuff like that. So, next one. Now the inclusions. Now inclusions are any solid material that's trapped in the weld that is not weld metal and or base metal. Now, why do I have to go? Now, if you read back into the book will tell you that it's any metallic material. And that's absolutely not correct. Because, first off, you guys have all seen it. You can have slag inclusions, right? Slag metallic? No. So we can have that. We can also have metallic inclusion. Excuse me, we can have non-metallic inclusions and metallic inclusions. Examples of metallic inclusions. If you get iron dust inside a aluminum weld, it'll break. Another one we're going to be talking about here in just a little bit is tungsten. Get to that when that slide comes up. But anything that's in that weld that is not base metal, that is not weld metal, is an inclusion. If it's a gas bubble, it's a gaseous inclusion. If it's sand, if it's dirt that fell down inside the weld, rust, paint that didn't burn out, all these are inclusions. If it's the wrong type of metal from some other form of contamination, in aluminum especially, if aluminum gets contaminated with steel, it will crack, it'll cause you nothing but issues. And so you can have metallic inclusions on top of your non-metallic inclusions. So next slide, classic stick weld, looks like 6013, where someone was long arc and got slag all the way through it. You guys have all seen this, you've all done this. And don't tell me you haven't, I know better. The next one, this is a V-groove with a huge slag bubble in it. And I've actually tried to recreate this thing. This, as far as I'm concerned, this is a work of art. Okay? Be on slide 16 here if you guys are keeping up here. That huge chunk of slag. And I have tried to do this. I don't know how they did this. I'm impressed. I really am. Because I've tried to recreate that and haven't even been able to come close. Now, next slide. Okay, now this one right here, this is in every single textbook out there, and it's wrong in every single textbook out there. Every textbook out there that has this picture shows it as being with lack of fusion, and that is exactly backwards. So let's talk about this. This is actually an X-ray of a weld. So how do X-rays work? Okay, when X-rays go or any sort of, this is probably actually gamma source. Don't need to worry about the distance. They all work about the same. They all work exactly the same way, just a higher energy level. But how do X-rays work? Well, think about how you guys have all had, if you've ever been to the doctor and had x-rays of your body. Okay, so what happens? Well, you stand there and they go and take a picture of your body by shooting x-rays into it. Some of them get blocked, some of them don't. Okay, what color does that film start out as? Okay, that film that's in there starts off as being white. And then as the x-rays or the gamma rays, whichever one they're using, hit that film, it causes it to get darker and darker and darker and darker. This is why areas that are less dense, let's say you get an arm x-ray, you know, the skin and the flesh and the muscle kind of goes away, looks kind of hazy, but your bones, being much denser, absorb more of that radiation, block more of that radiation, look bright white. So this picture here, with those bright white spots in there, they cannot be voids in the weld. Every textbook out there uses this exact same explanation, saying that, yep, these are actually holes in the weld, and that's wrong. This is what tungsten inclusions look like. Remember, tungsten is the densest element, densest metallic element that we have. And if you have a tungsten inclusion, especially if you're TIG welding in aluminum, it will crack. There is no way it can't, because that tungsten is so dense that it just sits there. Aluminum, very, very light, very, very soft in comparison, and aluminum is very, very thermally reactive. So as that weld goes and expands and contracts around that tungsten just sitting there like a nice little diamond inside there, and it can't move. As the weld squeezes around it, it's just going to crack. And once the aluminum starts cracking, it will keep cracking. Tungsten inside a weld, especially inside aluminum weld, is absolute death. And by you can increase the exposure time with an x-ray for this sort of thing, and we can increase our exposure time to the point where the weld just completely disappears. Those little pieces of tungsten that are in there will stand out just like little pinpricks, little stars in the sky. And so, like I said, I like pulling this one up because it's in our textbook. It's in every textbook I've ever seen, and it's labeled wrong every single time. All right, this last one I'm going to cover for today. I'll put up another, or at least on this video, I'll put up another one later. Inadequate penetration or lack of depth of fusion. Two different ways this can be described as. Okay, so inadequate penetration just means we didn't sink it all the way down to the bottom of the root. When you guys are doing your open root passes, which you'll see a lot more next semester, if that weld doesn't sink all the way through, that's inadequate penetration. The other thing is if we're doing a partial penetration weld, and meaning we're not burning all the way through, but we didn't get enough weld into it. The only way we're going to find a partial penetration weld, PJP weld, partial joint penetration weld, is if we're doing x-ray or UT on it. We got to have something that's going to be able to penetrate that weld and tell us where our depth of penetration is. Otherwise, it's got to be cut and measured. On a complete joint penetration weld, if we can find any of that root, now think about that when you guys are doing your butt joints, that's exactly what I'm looking for. This is going to be a complete joint penetration weld, and as long as we can find that, as long as it burns all the way through, you're good. Now, if you look at, so we're on slide 19 here, excuse me. If you look at the bottom picture there, you guys have all seen that if you've done your butt joint. If you haven't, trust me, you will. That's just a weld that didn't sink all the way through. Some other examples of inadequate joint penetration. First picture on slide 20 is welded from one side, didn't sink all the way through and cut. Second picture, we welded on both sides, but the welds didn't tie together. And the third one is we were trying to get it down to the root, and there's a big gap there. This is something you guys will see on your multi-passes if you were doing it way too cold. So, all right, I'm going to stop right here. We're going to leave off on arc strikes. I'm going to pick up with that one on the next session. If you guys got any questions on anything that I've talked about so far, please let me know. And I'll be uploading these during the week, so I'll give you plenty of time to look over this stuff. So again, if you got any questions, send me an email, leave a comment here, and I'll do my best to get back to you. Otherwise, have a great day.